Thank you. So thanks also to the Simon Center and the organizers for this invitation. So I should say that I gave a previous lecture at the center in this room a few months ago at the inaugural meeting, where I explained how I tried to develop a gauge theory picture of Khovanov Homology, but I didn't explain what the resulting picture was. So today I'm going to explain what, without really explaining how or why. I know there's a logical flaw, which is that the audience is different for the most part. I hope the talk will make sense anyway, without having heard the first one. So another thing is that I don't really want to assume that you have heard of Khovanov Homology before, but if you haven't, well, I hope the talk will again make some sense, but we'll have to see how well we can do. I will say, I explained this more fully at the beginning of last lecture, but there is a previous physics-based approach to Khovanov Homology. Some years ago, what I did was to try to develop more of a gauge theory approach, because after all, inasmuch as Khovanov Homology is a generalization of Jones' polynomial, and the Jones polynomial can be described by Chern-Simons gauge theory, I thought that Khovanov Homology likewise should have some kind of gauge theory description. And the last lecture was mainly about the obstacles to such a gauge theory description and how I tried to overcome them. But like I'll say, today we're really only going to explain what the answer was, rather than where it came from. So the story is going to involve some elliptic differential equations in 4 and 5 dimensions. And since the whole story is a little bit complicated, I'm going to introduce it in pieces. So one thing which we should remember at the beginning is the relation of the Chern-Simons function in 3 dimensions to the instanton equation in 4 dimensions. So in this talk, the gauge group is going to be a compact Lie group that I call G. And A is a gauge field or connection on a G bundle, where W is some manifold. If we want to talk about the complexification of G, we introduce it explicitly as G sub C. And likewise, if we have a complex connection or a complex complexified bundle, we call it curly A, a different font from the regular connection. The complexification of a G bundle E we call EC. And similarly, U and UC are the spaces of connections on a G bundle E or its complexification EC. And finally, all our elliptic equations are gauge invariant equations, and they're elliptic in the appropriate sense for such equations. So what is the Chern-Simons function? Well, if W is a 3-manifold, then a connection A on a G bundle over W has a Chern-Simons invariant, which, if the bundle is trivial, we can somewhat naively define by that formula, and that will be good enough for us today. To arrive at the instanton equations, we pick a Riemannian metric on the 3-manifold, and then we place the obvious Riemannian metric on the space U of connections. So, if delta A is a small displacement of a connection, we have the sort of obvious L2 norm on the space of delta A's, and that gives us a Riemannian metric on the space of connections. Then we take minus the Chern-Simons function as a Morse function on U, and we write the equation of gradient flow. I've introduced a time coordinate, which I've called S, because T will be used for something else in a bit. So the gradient flow equation says that the time derivative of the field, in this case the time derivative of the connection, is the gradient of the Morse function, or minus the gradient of the Morse function, in this case, the gradient of the Chern-Simons function. So, a priori, this won't be very nice. We have a 3-manifold, and now we're flowing for a connection on a 3-manifold. So we've introduced a 4th time direction, but the way it was introduced is completely asymmetrical from the first 3 dimensions. However, something nice happens. The equation of gradient flow turns out to have 4-dimensional symmetry. In fact, it's equivalent to the instanton equation on the 4-manifold M, which is W times R. The way this happens is that dA ds is the electric field in a gauge where A naught is 0, and the gradient of Chern-Simons is the magnetic field. So our equation becomes that E plus B is 0, which is a non-relativistic way to write the instanton equation. So, in this way, the instanton equation emerges as a happy accident, so to speak, in this derivation at least, from gradient flow with respect to the three-dimensional function. Of course, those of you who are all familiar with floor theory will know that this nice fact is one of the starting points in floor homology. Now, roughly speaking, we want to do the same thing for a complex Lie group, so that we can define floor theory for a complex Lie group. So, well, the starting point is okay. A connection on a G bundle has a Chern-Simons function. So remember, now we've got a complex bundle. The structure group is the complex Lie group. The connection is curly A. But the Chern-Simons function is defined by the same formula. Of course, it's now complex valued. To do Morse theory, we have to make two immediate changes. First, the Morse function is supposed to be real, but the Chern-Simons function is now complex valued. So we pick a complex number e to the I alpha of modulus 1, and we define our Morse function to be the real part of Chern-Simons times e to the I alpha. Well, that's a preliminary definition of the Morse function. We'll improve it in a bit. Now, a second thing is we have to decide what kind of metric we're going to use on the space of connections. So in the previous case, there was a completely natural metric on the space of connections. Once we picked a metric on the three-manifold.
Why do you choose the real part of this, not simply choose the model?
If you pick them up, nice things are going to happen. And they wouldn't happen if we do something else. The question was, why not take the absolute value of Chern-Simons? You can try that, but I don't think you'll like it. Now, the second thing to worry about is that there's no convenient metric on the space of complex connections that has the full complex value gauge symmetry. A metric's supposed to be positive definite, but it's hard to, there isn't any reasonable Riemannian metric that's positive definite and invariant under this non-compact group. So we're going to, instead, introduce an operation of complex conjugation and pick a metric on UC that will be Kähler, but it will be invariant only under the maximal complex subgroup, which is what we originally called G. So our metric is defined by the same formula as before, except that if we didn't introduce the complex conjugate, we'd get a holomorphic bilinear form, but it certainly wouldn't be positive definite, nor would its real part be positive definite. So we consider this Kähler metric by taking complex conjugating one of the two variables. So it's a reasonable metric, but it doesn't have the full complex gauge symmetry. Now we can write a gradient flow equation. We say that the time derivative of the complex connection is minus the gradient of the Morse function, where for the time being we can try this Morse function. However, we're usually interested in a complex connection only modulo complex value gauge transformations. And we've written an equation that does not have that symmetry, since our equation is only invariant under unitary or real value gauge transformations. So to compensate for this, one approach is to set the moment map to 0 and consider the previous equation only in the space of zeros of the moment map. In other words, we're on a Kähler manifold. The space of connections is the metric we wrote before is actually a Kähler metric on the space of connections. And there's a corresponding Kähler form, where I've written the complex value connection in terms of its real and imaginary parts. Where A is a real connection, and I've called the imaginary part I phi, where phi is in one form with values in the adjoint bundle. So having introduced the real and imaginary parts of the complex connection, the Kähler metric we introduced before has a Kähler form. And correspondingly, there's a moment map for the action of the unitary gauge transformations on the complex valued space of connections. So instead of simply considering Morse theory, an improvement would be to restrict the Morse theory to the space of zeros of the moment. A general fact about Kähler geometry is that the zeros of the moment map are invariant under the gradient flow, well, for this kind of Morse function. And so we can compensate for the fact that our metric was only partly invariant by restricting the gradient flow equations to the zeros of the moment. This is actually what I did in the first paper where I discussed these flows. But there's an improvement, which is to introduce another field phi 0 as a Lagrange multiplier. Phi 0 is a section of the real adjoint bundle, and we write an extended Morse function, which is just the old Morse function plus phi 0 times the moment map. What we've done is to add another variable, so now all the critical points of the moment map are at mu equals 0. And flows that start around the critical points will always be flows that happen at mu equals 0. So now, on the space of phi 0 fields, there's an obvious metric. And now, writing this kind of phi, capital Phi for the pair, the complex connection in phi 0, we write a gradient flow equation for this Morse function. And that better takes into account the complex gauge invariance we're interested in than the original version. Now, okay, we've written an equation which, just like in the first case, has no obvious symmetry between space and time. But something nice happens, just like in the real case. Well, the first thing that happens, which is nice, if you do this at random, you would not get an elliptic equation in 4 dimensions, let alone one with 4-dimensional symmetry. But here we actually get elliptic partial differential equations with full 4-dimensional symmetry. So they can be written like so, where t is a certain function of alpha. And plus and minus are the projections of a 2-form onto a self-dual and anti-self-dual parts. In 4 dimensions, a 2-form can be decomposed as a self-dual 2-form plus an anti-self-dual 2-form. And plus and minus, so for example, f minus phi, which phi is a 2-form, and then we take its plus projection. Similarly, dA phi is the exterior covariant derivative of phi. Phi was a 1-form, so dA phi is a 2-form. We take its plus projection, and likewise here. So this is a nice system of elliptic partial differential equations, and it has the full 4-dimensional symmetry. So the same kind of nice thing happens that happens in the more traditional case of Morse theory flow for the real transformance function. So these are elliptic partial differential equations modulo the action of the gauge loop for all t and Rp1. In other words, t is a real number or infinity. If t is 0 or infinity, you have to multiply one equation by t or the other one by t inverse. But the equations have a limit, which is still elliptic as t goes to 0 or infinity. I tend to believe that there will be an interesting monodromy around this circle, that is the Rp1. But that hasn't played any role, at least in my work so far. So one thing I should say is that these equations were actually first found by Kapustin and me in our work in geometric line lines. Although Yamron, in a paper written around 1990, was in the same general ballpark. Now, so to write the equations with 4-dimensional symmetry, what did I do? Well, we had what started as an imaginary part of the connection. So it was a 1-form on W with values in the adjoint bundle. But there also was a Lagrange multiplier that lived in the adjoint bundle. I combined the two into a field that I called phi, that takes values in 1 forms on M. I've used the fact that since the form manifold M was W times R, 1 forms on M are 1 forms on W plus R. So what has combined in writing the equations with 4-dimensional symmetry into a 1 form on M started life as a 1 form on W, and then we decided to add a Lagrange multiplier, which lived in the second one. And then it all combined together into an equation with 4-dimensional symmetry. So these equations can be the starting point for developing a floor-like theory for the complex Lie group GC. In other words, imitating floor, given a 3-manifold, you would, well, there's a Yang-Mills theory related to these equations. It's a version of n equals 4 super n-Mills. So as a physicist, you'd be studying twisted n equals 4 super n-Mills on a 3-manifold and trying to find the space of quantum vacuum fluids. The classical approximation would be given by a time-independent solution of these equations. And then there are the instantaneous corrections that would involve time-dependent solutions of these equations. So a physicist will be finding the quantum vacuum states of the first n equals 4 or the 3 manifold. A mathematician would simply be doing whatever Floor did, but starting with these equations instead of the instantaneous equations. So, well, you might ask me if we could do Floor theory for other real forms of G. For example, what would be Floor theory for SL and R? Well, if you look back at our equations, you'll see that they have an extra symmetry of T is 0 or infinity. If you reverse, if T is 0 or infinity, there's a symmetry under changing the sign of phi. Because, for example, if T is 0, this term drops out. This also drops out. So the first equation becomes even in phi, and the second becomes odd. For generic T, that isn't true. So you could project these equations on the phi invariant part. But that would not be very interesting if we do nothing else, because if we drop phi, we would just learn that f is 0. It's more interesting to also pick a real involution of the compact group, of the algebra of the compact group, and impose invariance under phi going to minus phi together with the real involution. That makes sense if T is 0 or infinity, and if you do that, you get a reduced set of equations that you could use to construct a Floor-like theory for any real form of G, not necessarily compact. I didn't discuss it in the paper because, at least at the time, it seems a little less natural. So, as I told you before, these equations were actually studied by Khovanov and me working on geometric line lengths. Roughly speaking, well, what did we do with these equations? Well, we considered a family of four-dimensional topological field theories, just like Donaldson theory, except based on these equations instead of these equations. And we showed that geometric line-length duality is actually formulated as an equivalence between the theories that arise at two different values of T. From that vantage point, geometric line-length duality is a consequence of a much more general statement, which is S duality that equals four superiors in four dimensions. So I'm skipping a lot of details because I don't want to give a lecture on geometric line-length today. But to properly understand it, you need to consider a complex parameter, not just a real parameter. That's one thing I'll tell you. Now, I don't believe that this four-dimensional theory gives interesting four-manifold invariants. And there may be a technical problem in defining them, analogous to Donaldson theory where V2 plus is 1. But in any event, in geometric line-length duality, four-manifold invariants are not the goal. Instead of invariance of four-manifold, one's interested in the structures that the same topological field theory attaches to two manifolds, namely categories of boundary conditions, and three manifolds, spaces of physical states or morphisms. And these are not affected by the technical difficulties that may affect the four-manifold invariants. The technical difficulties have to do with the non-compactness of the space of complex-valued flat connections, but here there are boundary conditions that cause those issues not to arise. Now, although this theory probably does not give interesting four-manifold invariants, the math literature gives a reason to believe in hindsight, and possibly in foresight, that it does give interesting non-invariants. So there's something called quantum geometric line-lengths, which to a physicist means that you put on the gauge theory theta angle and equals four superiors. So, as a physicist, I've done more quantum duals before, but anyway, in the math literature, it's quantum geometric line-lengths, and it's been related to quantum groups. But quantum groups are related to the Jones polynomial and similar invariants of knots. So possibly this should be made us think that the topological field theory related to geometric line-lengths can be used to compute the Jones polynomial. Now, having gotten this far, I should also mention the work of Caldas and Chemnitzer interpreting Seidel and Smith, whose work gave a possible clue that Khovanov homology is related to geometric line-lengths. I understood the second one a little bit better, so that was more of a clue behind my work than the first one was, but they probably both should be clues. Anyway, the picture, but as I said before, today I'm only going to say what picture I arrived at, rather than how I arrived at it. And the picture I arrived at for the Jones polynomial was like so. We take our four manifold. So we motivated the equations from Morse theory, but we're not exactly going to use Morse theory. Although we'll go back to it in a bit. We take our four manifold. We have equations that made sense in any four manifold, but we're going to look at them a little bit differently. We take our four manifold to be W times a half line. W is a three manifold, and R plus is the half line. Y equal to or greater than 0. For y going to infinity, we require the fields to approach a chosen critical point of the Morse function. The same Morse function we had before. So I guess we are using Morse theory. I shouldn't be so bashful. We have this Morse function here. This one. We pick a critical point of it, and we ask that at y equals infinity, the fields start there. So finding the critical point can be very concrete. For example, if W is a 3 sphere or R3, the only critical point is that A equals phi equals 0 up to a unitary gauge transformation. So that was painless. But in another example, you might have to work a little harder to find your critical points. The critical point is defined at infinity, but instead we place the knot at y equals 0. That is at the end point of R plus. So R plus has both a finite endpoint and an infinite end. We pick the Morse function at the infinite end, but we put the knot at the finite end. So the picture is like this. Here's W. Here's the half line R plus. Way over there, we picked our boundary condition, which had to do with the critical point. But the knot lives in the boundary. Now, the boundary condition at y equals 0 is an elliptic boundary condition that's a little bit involved to explain. So I'm going to postpone that for a bit. So just imagine that I've told you what the equations are, I told you the boundary condition up here. There's going to be a slightly tricky elliptic boundary condition at y equals 0. Yes?
What do you mean by not use the point 0?
What it means is that the boundary condition depends on the knot. Actually, I'm about to say that. The boundary condition depends on the knot, and on the choice of a representation R of the Langlands or dual group G check of G. So in this description, the only way that either the knot or the representation enters is that the boundary condition depends on it. The boundary condition is a little tricky away from the knot, but actually, I lectured about it at the Simon Center a few years ago for a different reason. I won't assume you were present for that. So I will explain the boundary condition later, but we'll postpone it for a bit. So I haven't told you what the boundary condition is, but otherwise I've told you what the picture is. For the next step, we imitate Donaldson this. We let an be the number of solutions of our equations with incident number n. Incident number is defined in the usual way as a multiple of the trace of f wedge f, where f is the curvature 2 point. Now we have to worry whether incident number is a topological invariant, because n has both a finite and an infinite end. But the quick answer, slightly oversimplified, but the quick answer is that the boundary conditions trivialize the bundle at both ends in such a way that incident number is a topological invariant. So then, having defined the incident number, we let an be the number of solutions for given n. Conjecturally, an vanishes for large enough n. This hasn't been proved, although there's a simple baby version, which is in my paper with Kapustin, which is that if there's no boundary, or a compact manifold without boundary, an is 0 except for n equals 0. So the proposal here is that when there is a boundary, a weaker version of that holds, and an vanishes if n is too large. It would really be nice to prove that. Then we introduce a variable q, and we define a knot invariant. So the an is the number in quotes. You have to count solutions with certain subtleties as in Donaldson theory, the simplest being that an isolated solution is weighted by a sign. For physicists, the sign of the Fermion determinant. So you suitably count the number of solutions, which gives a topological invariant. Topological invariant here means a knot invariant, because the knots enter the boundary condition. And then you form a not invariant, which is a Laurent polynomial with the ANs for coefficients. Yes?
The equation depends on t. As a function of t, you can start with t equals 0 infinity and count. Is it not smooth?
The counting of solution should be independent of t, because we have one. Oh, sorry. The boundary condition may have trouble with 0 and infinity, but basically, right, the counting, in general, the counting of solutions of a family of elliptic equations is constant. So you can vary t.
And with t equals 0, because we don't know.
I invite you to try to find useful simplification when t is 0. Not everything is known. The only useful simplification I know, I will very briefly tell you about at the end of the talk.
Another question. So AN
Yeah.
is actually the Bernoulli characteristic of the modular space. Right?
No. If you want, there's a long story by Witten in 1994 about the conditions under which AN is an Euler characteristic of the moduli space, but they're not satisfactory. If the moduli space is an isolated set of points, the Euler characteristic would be the number of points. But here, each point will come with a sign, 1 or minus 1. So you count the points with signs, and it does not give the Euler characteristic.
But maybe the number of solutions that are non-zero for our genders we cancel out.
Yes, but I would be optimistic that, in fact, well, without boundary, which I showed in our paper, that there are no solutions at all. And I'd be optimistic that the same is true with the boundary for sufficiently large. I prefer to say that conjecture. I would think somebody will get interested in that. So, if the Gould group is SU2 and R is the two-dimensional representation, this is supposed to be the Jones polynomial. In general, we expect to get the usual knot invariants associated with quantum groups and Chern-Simons stage theory. But our goal is Khovanov homology, not the Jones polynomial. After all, it was right in the title of our talk. So we can't stop here.
So can you just say one thing? So, do I understand correctly that what you gain by considering the complexified group is that we can formalize the boundary conditions we should formalize in the real case?
Well, that's one of the things we do. But if I was to repeat in the lecture about how I arrived at this picture of the Jones polynomial, the n equals 4 supernomial theory is crucial. And that's related to the complexified group. After all, everything works together. So.
Just a question. The reason you cannot formally do it for the real group is that you won't be able to formalize the boundary conditions. Is that right?
Well, you can't formulate boundary conditions quite like the ones we use, but of course there are other interesting problems that you can define. They won't give, as far as I know, they won't give the Jones polynomial, although I can make no promises there. Now, the way mathematicians say it is that going from the Jones polynomial to Khovanov homology means you're supposed to categorify the situation and associate to a knot a vector space rather than a number. Actually, a vector space with a group action that leads to the cubic. A suitable trace in the vector space gives back a number. The number was this number. It's not actually a number, it's a function of Q. So what mathematicians would say is that to knot K, you associate a vector space, which I call H sub K, and it has a Hamiltonian, a conserved charge. Oh, I may have this on the next slide. Maybe I should. But it was conserved charge Q, and the idea is that a trace in this vector space should equal the function we had before. So, as developed by mathematicians, there's a massive algebra. But if you're a physicist, what it means is that the picture we've just described has to be derived from a picture in one more dimension. So an explanation of that for physicists is the following. If the extra dimension is time, so for some reason, a certain story on a form envelope gave a number, the partition function. But if we magically had a 5-dimensional theory, where we had a time coordinate, and the reduction to the time-independent case is what we already talked about, then quantizing that 5-dimensional theory would give us a vector space, a space of physical states. And if we could backify the extra dimension on the circle, that amounts to taking a trace in the Hilbert space, this trace I wrote here. But on the other hand, if the circle is small, we really get back to the previous picture by a kind of dimensional reduction. To be more exact, what we want to find is a 5-dimensional theory where it's true that the reduction on the circle gives back the previous picture. That'll mean that the trace that comes by reduction on the circle will equal the Jones polynomial. And that's what we're actually looking for. It's what mathematicians call categorification. So, like I said, categorification just means that whatever you've already studied, you find a way to obtain it by reducing a theory in one dimension way. I should also say that what I just said was part of the intuition advocated by Frankel and Crane when they started talking about categorification in the early 90s. And it's also been described this way in a paper for physicists by Dupont a few years ago. So we're going to practice by categorifying something, namely the Casimir invariant. The Casimir invariant is an invariant of a 3-manifold W. By the way, when we categorify the Casimir invariant, we won't be saying anything new. It will just be practice for categorifying the Jones polynomial. When we categorify the Casimir invariant, I'll actually be repeating, more or less, from a slightly different point of view, the facts we started the lecture with. Anyway, the Casimir invariant is an invariant of a 3-manifold W, where you count up to gauge transformation, the 5 connections on a G bundle of the W. Again, the word count is in quotes because you have to count them with signs. Now, a 5 connection is a solution of a certain equation. It's actually not an elliptic equation, but it's part of a nonlinear elliptic complex. Just as for linear elliptic equations, it's sometimes convenient to fold the complex and reduce to the case of an ordinary elliptic equation rather than a complex. In this example, all that means is we introduce a section phi 0 of the adjoint bundle, and we replace this equation with the Homology equation, which is now an elliptic equation. So, the counting of solutions is exactly the same. Because if you assume you have a solution of this equation on a compact 3-manifold without boundary, an elementary argument shows that phi 0 vanishes. So the solutions are the same as the solutions of these. And the signs attached to solutions are also the same. But for us, it will be a better starting point to say we're counting solutions of this, rather than saying we're counting solutions of this. If this explanation here was too brief, but you've heard of the Homology equation, just assume what was our starting point. We're interested in the Homology equation in 3 dimensions. Well, we want to categorify it, which means replacing phi 0 by the covariant derivative with respect to the coordinate. Well, you see, if we do that to a random differential equation, we'll get a differential operator rather than a differential equation. For example, here's a differential equation. I've picked it at random. But anyway, like almost any equation involving phi 0, it has the property that if you replace phi 0 by d by s, you'll get a differential operator rather than a differential equation. But in this example, phi 0 only appears inside the covariant derivative, which is a commutator. In other words, the covariant derivative of phi 0 can be thought of as the commutator of the covariant derivative, exterior derivative, with the multiplication operator phi 0. And since phi 0 only appears inside a commutator, if we replace it by d by s, we at least will get a differential equation. Even when we get a differential equation that normally won't be elliptic. So, but in this case it is. So we replace the 3-manifold W by the 4-manifold W times R. We did that once already with a different explanation of why. R is parameterized by the time s. And we just replace phi 0 by d by ds wherever it appears in the equation. This makes sense for a reason I told you. The substitution gives a differential equation rather than a differential operator, because we started with an equation in which phi 0 only appears inside the commutator. We now replace this commutator by another commutator, and that's a component of the 4-dimensional curvature. So normally a procedure like this, even if it gives a differential equation, won't give an elliptic one. For example, if you play around with something like this, since I wrote something at random, I don't know what will happen, but usually it won't work. But in this case, we get back the instant time equation with a slightly different explanation than before of what we were doing together. What follows from this is that the Casimir invariant, which is a numerical invariant computed by counting solutions of a certain equation, can be categorified to fluid homology, in which a more subtle invariant, the vector space, is constructed, well, the way mathematicians say it is, starting with a chain complex that has a basis corresponding to the same solutions. If you're a physicist and you want to find the zero energy states of superhead theory on a 3-manifold, the starting point is to find flat connections, which minimize the energy classically. That gives a classical approximation to the space of zero energy or supersymmetric states. Then you have to calculate instant time corrections to get the exact answer. By the time you've done that, you've done what mathematicians say using these words. So now we want to categorify the Jones polynomial, which from the point of view of the present lecture is the invariant associated to counting solutions of these equations with certain boundary conditions that I haven't told you about. On a generic 4-manifold, we can't categorify this invariant because there's no candidate for the field phi 0 that should be replaced by d by s. So the invariant you get on a generic 4-manifold, if you can define this invariant, it's the numerical invariant that's related to geometric line lengths. So it can't be categorified by this method because there's nothing you would call phi 0. However, let's go back to the case where n is w times r plus, which anyway is the case that was relevant to the Jones polynomial. In that case, we have the same decomposition we used before, that a 1 form on n is a 1 form of w plus a trivial 1-dimensional summand, 1 forms of r plus. And the part of phi associated with the second summand is the field phi 0 that at the beginning of this lecture was introduced as a Lagrange multiplier. So now we categorify. We introduce a 5th dimension with a coordinate s, and we replace phi 0 by d by s. That was fairly painless. And you can tell your friends that you've categorified. You don't even have to know what a category is. So in this way, we get a partial differential equation or a 5-manifold that happens to be r, the time direction, times what it was before, which was w times r plus. So generically, as I keep telling you, this type of procedure won't give an elliptic differential equation, but in this case it does. Moreover, in a special case, we get full 4-dimensional symmetry. If t is 1 or minus 1, then the 5-dimensional equation that I described can be naturally formulated on n star times r plus for any 4-manifold n star. We get 4-dimensional symmetry, but it's not the 4-dimensional symmetry we started with. We started on a 4-manifold w times r plus. We had specialized an equation with 4-dimensional symmetry to w times r plus. But we specialized and categorified it. The categorification broke the 4-dimensional symmetry. by treating R plus differently from W. And then we introduce a new coordinate, and we get a new four-dimensional symmetry that relates W, which is the new coordinate. So it's another example where an unexpected symmetry appears. Here it appears precisely if t is 1 or minus 1. So we still get an elliptic differential equation for other values of t. So the definition of floor theory or the invariance gotten by counting solutions makes sense if we're on R times W. But if you replace R times W with a generic m star, you'll have to be at t equals 1 or minus 1. If you want m star to just be a four-manifold, oriented four-manifold, I should say, with no additional structure, then t should be 1 or minus 1. Now, I didn't yet explain the four-dimensional boundary condition, but it can be categorified. What that means is that the five-dimensional operation has a boundary condition, which if you take the fields to be independent of S, reduces to the four-dimensional boundary condition. The boundary is now a four-manifold m star rather than a three-manifold W. And the categorification of the knot becomes a two-manifold. We had a knot in the boundary, but now the boundary has an extra time coordinate. So it's up to us what to do, but what we want to do for Khovanov homology is to take a boundary condition that depends on a two-manifold embedded in the boundary. And the sense in which the new boundary condition is a categorification of the old one is that if both the boundary and the knot, the two-manifold, and everything else are time independent, then the boundary condition reduces to what we had before. The one we would have used to study the Jones problem. So the picture now looks like this. We're on a five-manifold, which is a four-manifold. In our original derivation, by categorification, the four-manifold was R times a three-manifold. But since there's four-dimensional symmetry, I've drawn it more generically. Well, assuming T is 1, I've drawn it more generically for general M star. So we're on a five-manifold with M star times R plus. There's a Riemann surface in M star. There's a slightly subtle boundary condition here. And it has a certain generic form away from sigma, but it's modified over sigma.
Is M star now compact?
It can be. It doesn't have to be. I drew a compact. The question was whether M star is compact. I said it can be, which is what I've drawn, but it's like Donaldson. It's up to you what format we're doing. Now, to get the candidate for Khovanov homology, we specialized in a time-independent case, which is what we got from our derivation. M star is time times W, and the surface is time times a knot. And then we exactly imitate what Floor did. We have 5 to 12. If you're a physicist, we're now doing five-dimensional super-animals theory, which we think of as a low-energy limit from a well-defined six-dimensional theory. We want to find supersymmetric vacua. We do it approximately by finding the time-independent supersymmetric states. And then we include instanton corrections. It's, if, yes, it was twisted to preserve a little bit of supersymmetry. Well, it preserves as much as it can. If there's a knot, it can't have full length invariance. If M star is R4, then we have four-dimensional length invariance. But we don't have five-dimensional length invariance. There will not be a symmetry between the R plus direction and the over 4. It's the wrong twist. So, for physicists, what we're trying to do is to find the supersymmetric bound state in a certain situation. The way mathematicians would do it by analogy with 4. We define a chain complex which has a basis given by the time-independent solutions. But we know what the time-independent equations are. They're the ones we categorified to get to 5 dimensions. So the time-independent solutions are exactly the solutions that we have to count to calculate the Jones polynomial. That's why the Euler characteristic of the chain complex we're about to find will be the Jones polynomial. The differential in the chain complex is constructed in a standard way by counting certain time-dependent solutions. So I haven't even written the five-dimensional equations. They're the ones you get from here by categorifying, in other words, replacing phi 0 by b by s. So to define the differential in the chain complex, we count solutions of the five-dimensional equations that interpolate between given four-dimensional solutions in the past and the future. In setting it up, we use the fact that the five-dimensional equations can themselves be interpreted in Morse theory in terms of gradient as well. So the formal structure is exactly like floor theory.
So if it's R4, the five-dimensional theory will get the extra formula, but this T will disappear. Or it can...
What will disappear?
The T part.
It only disappears if you want it to. Okay. Well, it depends on you. The question was what happens if you're not to win. And the reason something could happen is that if there's no knot, there's a lot more supersymmetry. But the more interesting case is that there is a knot, and generically the knot will completely break the supersymmetry to what we would have had in my presentation. Only one supercharge will be preserved, and you have to make a choice in setting it up, and that gives the key parameter. So the homology of the differential again here is the candidate for Khovanov homology. Now the candidate Khovanov homology is E times E graded, just like the real thing, where one grading is the cohomological grading. That's mathematical terminology. Physicists would say that there's a U1 conserved fermion number, and one grading is by the fermion number of this case. The second grading, which is sometimes called the Q grading, comes from the incident number integrated over an initial value surface. So an initial value surface is what we get if we set the time to a constant, like 0. So the initial value surface is W times L plus. So the incident number is the same as it was when we were computing the Jones polynomial. Now, W times R plus is not compact and has a boundary. The second fact is actually more important here. Because there is a boundary, the definition of the Q grading has subtleties. You really need to pick a framing of the boundary and also a framing of the knots. And these subtleties precisely match the framing anomalies of Chern-Simons theory. Now, we're not limited to the time-independent case. We can consider a more general sigma, such as I've drawn here. So I picked a knot, and, well, I, in this lecture, refer to knots, but our knots could be replaced by links. Mathematically, a knot is an embedded circle, a link is several embedded circles. Everything I've said for knots is true for links. Here I picked a link in the past that was an unknot, and a link in the future that was two unknots. Time is running vertically. And I picked a sigma that in the past was time independent with an initial length k. In the future, it's time independent with a final length k prime. And then I picked a very simple sigma that interpolates again. I picked unknots just because it was easier to draw, but the links in the past and future could be more complicated, and likewise sigma could be more complicated. Whatever they are, this picture makes sense. And by solving the five-dimensional equations in this situation, and counting solutions, and weighting them by the incident number and fermion number, we get what in Khovanov homology would be called the knot cobordism. Or I should perhaps say the picture is called the knot cobordism. We get what in Khovanov homology would be called the morphism associated with the knot cobordism.
So that's what the chain map?
Yeah, in floor homology, that's a chain map. For physicists, the fact that it's a chain map means that it commutes with the supercharge, which means that the whole picture is Q invariant. So if the initial state is Q of something, so will be the final state. So it's a linear transformation that commutes with Q. Yeah?
The instrument number is to be computed in fixed time size.
That's right.
But if it is changing with time,
Well, if the boundary conditions are tiny, that's a very good question. The question is, what? I'm not sure what level of knowledge of Khovanov homology is going into the question. I'm going to give an interpretation of the question. So the question was, I'll take the question to be whether the incident number changes in time. Well, on closed form manifold, of course not, because it's topological invariance. As long as our boundary condition is time independent, the incident number is independent of time for the same reason as on a closed form manifold. There was some subtlety in defining it, but once we define it, it's time independent. When we draw a non-cobordism, the boundary condition is time dependent, and actually the incident number changes in time in a way that depends upon the Euler characteristic of the non-cobordism as well as the normal number. This matches standard facts of Khovanov homology. I'm not sure. Well, hopefully that's reasonably close to answer the question. So I'd like to at least tell you something about the boundary conditions, but actually it's too subtle a story to be compressed into the available time. Although I'll tell you a little bit more if there are questions. But at least in the slides I've prepared, I'll only tell you precisely the boundary condition away from those. Well, I fear that I might have the wrong version of this talk, because on Sunday I removed an inaccurate time of the Zoomcast. But it seems to have come back, so maybe I have the wrong version of the time. And so I'll have to make a similar operation later on. So to explain the boundary conditions, I need to tell you about one of the important equations in gauge theory, in mathematical physics related to gauge theory. That's Nahm's equations. So the reason I'll be talking about Nahm's equation is, what is a boundary condition? We need to know what happens near y equals 0. Well, y is the normal to the boundary. So there's the local picture is essentially one dimension. We're not really interested in what happens along the boundary. But something funny is going to happen normal to the boundary. And what will happen normal to the boundary will be governed by a one-dimensional equation, which I have to tell you about. It's called Nahm's equations. Nahm's equation is a system of ordinary differential equations for a triple x1, x2, x3, valued in the third tensor power of the Lie algebra of G. And the equations read like so. dx1 dy plus x2 commuted with x3 is 0, along with cyclic permutations. The equation is invariant under SO3, rotating x1, x2, and x3 over the length of the on a half line of y greater than 0, Nahm's equations have a special solution, where x is a fixed matrix divided by y, where the t's are elements of the Lie algebra that evade the SU2 combination relations. So if you try it, you'll see that this term is of order 1 over y squared because it's quadratic. But this one is of order 1 over y squared because you take the derivative of 1 over y. And the combination relations are just right to make the equations work. So this gives a special solution of Nahm's equations. Now we could use any elements of G that obey the combination relations, and probably the generalization is important. But the most direct way to get Khovanov homology involves the case that the keys define a principal SU2 algebra of G in the sense of clusters. If you don't know what that is, it roughly means that you take an irreducible embedding of SU2 into G. So I've just described a singular solution of Nahm's equations. It might sound very special, but it actually plays a large role in a lot of things. Nahm introduced it in his original work on monopoles, and it was much developed in later work by Khovanov and others. Here we use it to define an elliptic boundary condition of our equations. Well, we use it to define a boundary condition. And then, remind me, a few years ago here at the Simon Center, I lectured about what I did with the Barratza, where we use this kind of boundary condition in 4 dimensions. But today we'll be doing it in 5 dimensions. So, I actually, although it works in the categorified version for brevity, I'll just explain it in 4 dimensions. So, Nahm's equations can be embedded in our 4-dimensional equations. So, unfortunately, I don't think they've written down the 4-dimensional equations. slide, but we look for a solution of the four-dimensional equations. I've just written the beginning of the equations. Well, actually, I wrote the most important things. We look for a solution that's invariant under translations of arc length. The connection vanishes. Phi is a pullback from arc length. The component phi in the y direction is 0. Then, see, from here, f, the curvature drops out, and all the derivatives drop out except the y derivative, and we reduce to Nahm's equations. Yes, for brevity. We can do this in a minute. Well, Greg has correctly pointed out that I wrote the t equals 1 version of Nahm's equation. But there's a similar embedding of a solution of Nahm's equation for any t. So the Nahm pole gives a special solution of our equations. We define an elliptic boundary condition by declaring that we only allow solutions that are asymptotic to this one for y going to 0. This might sound unfamiliar as an elliptic boundary condition if you're accustomed to Dirichlet and Nahm and similar things. But if you actually look up a textbook definition of elliptic boundary condition, this is one. I won't try to explain that right now. But this is possibly not the type of elliptic boundary you usually consider, but it's an elliptic boundary condition by a standard definition. So this is the boundary condition we want in the absence of knots. As for y going to infinity, well, if we want to get Khovanov homology, we simply require that everything is 0 as y goes to infinity. Now, in the absence of knots, I expect that the special solution I described is the only one. This would correspond to the Khovanov homology of the unknot being a frank one. The chain complex would be one-dimensional with one generator corresponding to this one explicit solution. And since there's only one solution, the differential would be 0 and that would begin with. As a physicist, you say that the ground state is unique and there's nothing compels it. Now, this is the candidate for Khovanov homology of the unknot, but there's a variant of this that makes some things clearer. You can understand this better with some knowledge of Nahm's equations. Let T be the Lie algebra of maximal torus of G, take a triple of elements of T, and then we modify the boundary condition for y to infinity, so that the connection still vanishes, but phi approaches the C up to gauge transformation. So that's a new condition that we use at y equals infinity. One hopes to show that this deformation of the boundary condition does not affect the counting of solutions. You'd expect that on general grounds if the counting of solutions is well behaved. Continuously varying some of the parameters, hopefully, doesn't affect the counting of solutions on the elliptic equation. Because of the non-compactness here, you could worry that something will move off to or from infinity. So there is something you need to prove to show that this is well behaved. As a special case, according to Khovanov, Nahm's equations have a unique solution with this boundary condition, with the same behavior of y equals 0, and the deformed boundary condition at infinity. And in the deformed, and for some purposes, much simpler description, this solution represents the Khovanov homology of the unknown. Now, the boundary condition I described for the case that the boundary is R3 has a direct analog for any three non-boundary boundary. Do I have any time at all? 0? I'm going to borrow 2 minutes. So there's a small twist. The restriction of the bundle over M, instead of the connection being 0, the connection on the boundary is the Riemannian connection of the boundary. And then you find that the solution with the non-pole can be adapted and defined in elliptic boundary. There's an interesting point that we'll have to skip, which is that because the tangent bundle of the boundary is not trivial, you run into a framing anomaly that matches that lecture sign.
Sorry, are you talking about SO3 gauge?
Well, for brevity I said impressively, but there's a simple analog for any G, with the principal embedded with the tangent bundle of G. Now, the boundary condition is modifiable or not. I don't have time to explain it properly, and since our chair is timed yet, the times given negative. Perhaps I shouldn't say anything at all. I'll just very, very quickly say that just like the boundary condition without noise, the boundary condition with noise is defined by explaining locally what it is. The local model is that the boundary looks like R3 and the output looks like R. And the boundary condition is described by getting a singular model solution that has the usual non-fall away from K, but has some other behavior on K. And then, since it's all invariant under translations along the knot, it reduces to equations in 3 dimensions. So you find, in this situation, a special singular solution. This is R2. So R2 is the 2 dimensions transverse to a knot. This is the usual R plus. There's one point on the boundary where there's exceptional behavior. And you're supposed to find, for every representation, every highest irreducible highest weight module of the dual group, you're supposed to find a model solution of my equations in this situation, which in some sense is related to the Hecking transformations of geometric modes. So I think I'll have to resist explaining that in any detail, perhaps postponing it and for additional developments. Well, we get another edition. Thank you.
Is there some limit in which it's related to Seidel-Smith when they kind of hold a bunch of curves? In the
Well,
same way that you could have like
well, what I can, okay, first of all, with Gayasha we're working on most approaches to Khovanov homology, in some sense, are based on assigning a category. I'm going to skip most of the slides, but I do have a picture that a lot of people haven't seen this before. You stretch a knot in one direction, so that there are some jumps, but generically it's independent of one point. And you try to piece things together by starting with the solutions in 2 plus 1 dimensions. Now, there's something really nice. The only really nice thing about these equations I know of is that in 2 plus 1 dimensions they simplify geometrically and have a nice interpretation in terms of complex geometry. It's actually what I've been, some of it is in my paper, but we can go into it more deeply. So, your question was about Seidel-Smith. And you can do this in a way that qualitatively makes contact with Caldas and Chemnitzer, or whatever kind of details. But Caldas and Chemnitzer are studying a B model, which will not have manifest 4-dimensional symmetry. I didn't explain that approach. First of all, we're taking more of a physics lesson. But secondly, I wanted to give you manifest 4-dimensional symmetry. For manifest 4-dimensional symmetry, you want an A model, as in Seidel-Smith and partially interpreted by Chemnitzer and another paper. I believe that in most of that work, it's hard to see the Q grid. So qualitatively, this is similar. The very tricky boundary conditions in the 5th dimension are helping us get the Q grid. That's the best answer to give quickly that I can see. Well, we have a lot of fun with this. We have Hitchin's equation with point singularities. We have O pairs with trivial monotony and the Godin model. All kinds of fun things. In fact, in a sense, the lecture was an outlier for this week's conference, but it's analytic continuation to the second sheet. We'll pick that up.
So, also going to ask about Caldas and Chemnitzer. So, I have some question. You mentioned that Caldas come to work with the B model.
Yeah.
On the other hand, what they do is they categorify maybe dimensional representations. And the way the actual representations appear, they appear through homology of
Right.
shapes on defined correspondence, which actually has to do with the A model in terms of probabilities. Right? So, what is
Well, we're allowed to do a B model without target space. See, I was able to give a reasonably self-contained explanation for mathematicians today because we focused on the A model, which had manifest 4-dimensional symmetry. So it didn't really require a physics lesson. In the work of Caldas and Chemnitzer, it's extremely beautiful, and I really want to understand how it comes out of this. But it's related to what I'm describing by mirror symmetry. The mirror symmetry question has a natural interpretation started in 6 dimensions, although some details aren't that clear. But you see, that will not be the approach that will make 4-dimensional symmetry manifest, just as it is not manifest in the work of Caldas and Chemnitzer. Caddis and Kempster define a variety of elementary moves and show the integrated relations. And I think that's the right answer in the D model. Whereas I'm claiming that in the A model, there are a lot of technicalities. You add a fifth dimension, do some crazy boundary conditions and so on. But eventually the A model becomes manifestly infinite.
But is it, from the point of view of the A model, is it easy to explain how to get different categories?
Well, that would actually belong on the second sheet.
Okay, maybe we can, you take one more question?
Well, you're the chair.
Negotiate. Yes, last question.
So, the limiting conditions is y goes to infinity.
Yes.
Do those simplify into anything that we know about on an arbitrary three-manifold, or?
Well, yes, they simply correspond to a complex life condition with a mild stability condition, the same one that was studied by. Okay. Yeah, right. Correct.
Thanks.
I'm going to study Khovanov Homology.
Yeah, right.